What's up guys, this is Andrew, your computer science teacher for today, and in this video we are going to solve the maximum size square full of ones. So without further ado, let's take a look at the statement. As the name suggests, we are given a matrix which is binary, alright, so full of 0 and 1's, and we should find the maximum size square full of ones, right? In this example we have a matrix with 6 rows and 7 columns, and the answer is 3. We have multiple squares with size 3. This can be an example. Right here. This can be another example. Let's say we can say here, yeah, this one too, alright, and so on. But if we try to look for a square with size 4, we won't find it. So the statement is pretty straightforward. We are going to start looking for brute force approach solutions, and there are a couple of them. All of them are based on the idea that we should try every bottom right column, right? So we should fix every cell from this matrix and suppose that this cell is going to be the bottom right cell of our square, and then find the maximum size for that cell. So for the brute force, we can fix every cell, alright? So we have for now n crossed m cells, and for each cell, the first brute force approach could be to make another for loop and try out each size of square, right? So if let's say I fixed this cell, I can try, okay, size 1. I have to check if this square is full of ones, and obviously we are going to do that using the partial sums. Then I should try, okay, for size 2, let's try this square, it's valid, okay, continue. For size 3, let's try this cell, it's valid, okay, continue. For size 4, it's not, so the answer for this cell is going to be 3. This brute force approach is going to have n crossed m cross, let's say, n time complexity, right? Right. Now, we can be smarter about this, and we can notice that every time we fix a cell, instead of iterating through every possible size of the square in that cell, we can binary search it, right? Because for a couple of sizes, let's say, it's going to work, right? And from some point it's going to not work, right? So this is good, this is good, this is good, this is good, and now it's not, right? And when we do the binary search and we try out the middle size of the square, we just go in that square and take its sum with the partial sums, and if it's full of ones, that means it's valid. We can look for a bigger one. If not, we will look for a smaller one. So this is another brute force approach, which will have time complexity of n cross m cross log. But these two are not optimal, obviously, because our optimal solution is going to have time complexity of big O of n crossed m. And let's see how to do that. Well, first of all, we are trying out each cell. And for each cell, when finding its answer, we are starting over again and either iterating, either binary searching. But we don't use the important fact that when we are in some cell, we have already computed the answer for other cells. So we can use those answers in order to compute the answer of the current cell. So after computing the answer of some cell, we are not going to ignore it. We are going to store it in memory. And for that we are going to use an extra two-dimensional array. And that information is going to be used in the future to compute the answers of other cells. So let's call our extra two-dimensional array, let's say maxlen. So here I have maxlen of I and j, right? And obviously maxlen of I and j is going to be the maximum size, right, of the square, alright, which has with the bottom right corner, in the cell at row I and column j. So let's call our extra two-dimensional array maxlen of I and j, and maxlen of I and j is going to be the maximum size of the square with the bottom right corner in I and j, and obviously full of ones, right? So now when I am at some cell ij, alright, let's say this cell for example, when I am here, I know that I have computed the answer for each previous cell, right? So for all these cells, which is super cool because I am going to use their answers in order to compute mine in constant time. Well, for this cell, let's say, if I want to compute the maximum size of each square, right? Let's say in this case is going to be 3, right? Well, in order to have here a square of size 3 with this bottom right corner, I need to have 3 things. I need a square of size 2 with the bottom right corner here, in this neighbor. I'm going to need another square of size 2 here, so with the bottom right corner in this neighbor, and I'm going to need the third square full of 1's of size 2 in this neighbor, right? So if let's say this is going to be my square full of 1's, right? And this is me, and this square is going to have size L. Well, first of all, I'm going to need a square here, alright? So on this neighbor, I'm going to need a square of size L minus 1. I am going to need then here in this neighbor a square of size L minus 1, right? So something like this. And the third one, I'm going to need here in this neighbor another square of size L minus 1, full of 1's, right? So obviously max len of I and j is going to depend of these 3 values, right? This neighbor, and this neighbor. And how it's going to depend? Well, obviously it's going to be 1, right, for completing with this cell, plus the minimum of those 3. Minimum of. And I have max len of I minus 1 and j, the first neighbor. Max len of I and j minus 1 and max len of I minus 1 and j minus 1. And that's it, guys. This is how we compute in constant time the answer for the cell at row I and column j. Now, this being constant time and having n cross m total cells, I am going to have the optimal solution in big O of n cross n. So we are basically having 2 nested for loops. The first one for the row from 1 to n, the second one for the column from 1 to m. And for each cell, if it has a 0 in it, alright, the max len is obviously 0. If it has a 1, we will compute its value, its max len, using these 3 neighbors that are already computed, right? And we are taking the minimum of these 3 sizes and adding 1. Now, I really hope you understood the solution. It's time to clean the whiteboard and write the code for it.